Muy buenas tardes, bienvenidos todos a la última versión de este año del seminario del doctorado en Ingeniería y Ciencias con la Industria. Hoy día tenemos el placer y el honor de contar con el profesor Opher, que es el Distinguished Professor of Operations Management at the Rotman School of Management at the University of Toronto, co-founder and CEO of SiMLQ. And Opher is a distinguished professor of operations management at the Rotman School of Management in the University of Toronto, co-founder of SiMLQ. He has visited an associated professor at Industrial Engineering and Management of Tachyon and visited professor School of Management and Engineering at Shanghai University of Finance and Economics, and served in multiple areas. He has a PhD in operations management from the Sloan School of Management at MIT, and an MBA and a Bachelor of Science in Industrial Engineering at the Tachyon. He researches on simulation and on different aspects, and today he's going to give our lecture, Queuing Analytics, Machine Learning, Casual Queuing, and SiMLQ, or Data-Driven Simulation. Opher, thank you very much. All yours.
Thank you guys for the introduction, for having me here. It's a real pleasure so far. Let's see if it will stay the same after this. I don't know any Spanish. Mucho gracias was kind of the highlight of my Spanish. After living in Canada for just over 21 years, my French is limited to bonjour, so you're in obviously, having Juan Carlos here is a treat. Right, when I started my PhD, he was the one who welcomed me, so Sol and Juan Carlos kind of hosted us and ease us in as much as possible to ease Israelis into the winter at MIT. I mean, I'll put it that way. Also, my talk today is a 90-minute talk, but I'll try to squeeze it in an hour, as that's the time I have here. So if I skip some things, please forgive me. And I also do something which you shouldn't do if you're going as a PhD student to the job market. I'm talking about essentially 3 different papers or research projects. When you go to the job market, talk on 1. If you talk on 2, you're in bad shape. So that's what I will do. This is joint work with a group of people. First of all, my colleagues Dmitry and Arik. And second, Mark and Zhenghang. Mark is from Berkeley. Zhenghang is our PhD student. You'll meet him later today during the presentation, don't worry. And this is going to be the middle part of my talk. Eliran and Krass are contributed to the first part of the talk, the machine learning usage in queuing. And Shany contributes to everything we do, including in SiMLQ. So those are the co-authors of these papers. And I want to start with a little bit of context on queuing systems and why do we care about them and what do we teach in them. So MG1Q is kind of the most basic queue that is realistic to some extent. MM1 is really a cooking example that allowed me to get tenure. I'm not discounting it. But MG1 is a much more sensible model. And the trick is that we know how to solve MG1 nicely, but when you go further and you look at the GG1, you don't really know how to solve it. And even our solution of MG1 is not great. And then the question is, especially for us who wants to do optimization afterwards, can we find a really quick solution for a GG1 such that when I do the optimization, I will not be able to take derivatives and do closed form solution, but my search for the solution is going to be really quick, right? If you give me a GG1 now, I can solve it. I can solve it very accurately, but it's going to be numerical and it's going to take a lot of time. So when I do optimization and I change, say, the capacity of the server, now I need to go and run my GG1 numerical work again. It takes a lot of time. I cannot do this. Machine learnings are really famous in being able to do this fast, this prediction fast. So what we've done here is essentially took a GG1, solved the ton of them, and then put a nice neural network on this data. I tell you, hey, predict what's going to happen. So the distribution of the number of people in the queue is our solution. You can get other performance measures out of it. So it works really quickly, really well, very accurate. The GitHub has the code. If you ever want to use a GG1 just to get very good predictions of what you do, or you want to optimize it, this is the best way of doing this now. It's the quickest way of doing this, and it's very accurate. Here is an example of how accurate it is. This is 10 random kind of experiments, square coefficient of variation for the arrival and the service times. Overall, our error is less than 0.5%. And if you look at specific percentiles, 25 percentile, the number of people in the system is 25% smaller than this, 50, 70, even 99.9, which is the tail distribution, which is traditionally hard to do. And you have better ways of doing the tail distribution with approximations, the traffic approximations that are nice, and you can do optimization of them. So you don't need this. But even there, we are less than 10% away from the result. So it's extremely accurate, very easy to use. Obviously, it takes no time to get a solution. Remember this, I'm going to be using it later in my talk. In my main talk, I'm going to be back to this. So this is this part. And the next common extension is to have the arrival rate to be time dependent. So if you think about most of our real life examples, you're going to have a state dependent arrival rate or time dependent arrival rate. You think about, emergency department, an example that I will use several times. At night, arrival rate is low, 10 a.m. it's higher, 6 p.m. it's higher, right? So we have this kind of seasonality or daily fluctuation of arrival rate. Every service that is closed at night, most of services are closed at night, right? You have this kind of different arrival rate. So GTG1 is a really important extension. We run the same thing. We get it. We use a little bit of a different configuration because we needed to know where you are and where you're going to. So we use some LSTM. It works very well, better than some other modern approaches. This is just an example. Again, 4 or 5 different systems. You see the predictions, you see the real one. The ground truth is from simulation, right? This is not, I don't have a ground truth solution here. And it's extremely accurate as well. So we nailed down those 2 problems. So when you talk about a GT, you need to carefully define this time-dependent arrival process. Take a look if you need to do this and see what we've done, if it works for you. So this is great. We know how to solve these 2 types of queuing, and you can think about how to use similar approaches for more complex queuing models. Admittedly, this is not theoretically very interesting. So if you think for a moment of what I described of what we've done, it's a very brute force method. I solved 10,000 systems. And now when I have the solution of the 10,000 systems, I tell you, hey, come and do some prediction, even linear interpolation between those solutions will give you a sensible solution, right? We do something a little bit more sophisticated, and it's sexy to say we use neural networks, right? We need to sell our stuff, but it's not really between us, not outside of this room. It's not really as groundbreaking as it looks. Because at the end of the day, it's a lookout table, right? A more sophisticated one. You need to carefully design the sample space and all of these wonderful things. And there are some theoretical components. So we use the moments of the distributions as input to our prediction models. In the GG1, we need 5 moments. In the GTG1, 4 moments are enough to get accurate results. But this is kind of the main thing. I feel it is more a computer science approach of, does it work quickly? And the answer is yes, it works quickly, very accurate. So when I want to do optimization, it's the way to do it. Make sense on this, guys? Very, very simple. Just wanted to start with telling you a little bit of this. Okay, the next part of my talk is the central part of the talk. It's called causal queuing models. And before I dive into this, let me take you for a second to some thought process on management analytics. I don't want to use the whiteboard because I don't see Lords here, but don't worry. So think about the time axis where we have the present and the future. Let's make it here. So we have the past and the future. The present is a thin line in between them. And we have on the x-axis, we have existing systems and non-existing systems to be systems. So in these 4 quadrants, if you wish, I only have data here on the past on existing systems, right? Machine learning models are really good in doing predictive analytics. They take me up, they say, oh, what will happen in this system? So last Monday, I've seen 70 people coming to the emergency department. Next Monday, it's a snowy day, I'll see 75. It's a good predictive model, can do this really well, but this is kind of in the current system. The trick for managers is what happens when I change the system, right? And when I change the system, say I bring another doctor and now waiting time are significantly lower, okay? So first of all, I can tell you, with another doctor, how lower are your waiting times? I don't know. It's a different system. I've never observed it. I don't have data on this. So there's causality that you need to capture as you move from the existing systems to be systems. The other thing that you need is to consider in this comparative analytics, that we have descriptive analytics in the past, predictive analytics in the future, comparative analytics in the past as in the future, counterfactuals. What would happen last Monday if I had another doctor on the floor? What would happen next Monday if I have another doctor on the floor on this different system? I want to be able to do this comparative analytics. And only then I can tell you, look, a doctor cost me $1,000, does it worth it? So the prescriptive analytics come after I do that. So with these 4 quadrants of descriptive, what I look in the data and describe what happened in the past, predictive, the same systems in the future, comparative, past and future, different systems, causality is important here, and prescriptive, which is the optimization, the holy grail of analytics, management analytics. All I want to do is to impact the world and put it to a better place. So with this in mind, what I'm going to do, I'm going to talk about causal queuing models. So models that allows me to take my data from the existing systems and do comparative analytics, what would happen in a different system. And I need to have these causal models, right, in order to be able to do this prediction because I'm changing my system. And that's what I'm going to be talking about. Okay, so I'm a queuing theorist. And I know how to do comparative analytics, performance analysis in queuing systems, you know. A favorite one, basically I'll ask you, hey, what's the arrival process? Oh, it's a Poisson or a general time dependent, right? All of these wonderful things. What is the service process? General time dependent, whatever. And then I can do analysis of this queuing system. I know how to do it. And when I don't know how to do it in closed form, I can use approximations or numerical methods, my wonderful machine learning algorithms that I just mentioned, right? I know how to do all of these wonderful things. And if I have data, what I'll have to do, I'll have to look at the data and I'll have to estimate, you know, oh, what is the lambda? Or what is the mu, right? What is the arrival rate? What is the service rate? I can use this. I plug these estimates, these parameters into my wonderful queuing models, and I'll give you a solution, right? I'll do the comparative analytics this way. You know, I have MM1, expected waiting time, I don't know, 1/1 minus rho, right? I can do the, give me the lambda and the mu, I'll find the rho, and if you change mu, you change the rho, I can tell you what happens. That makes sense? That's what a queuing theorist does. Now the question is, can I take this data that I used as a queuing theorist and do this comparative analytics without being a queuing theorist? So can I give it to my data science students who don't know queuing as well as I do? You know, I put 30 years of my life into being a queuing theorist, right? Can they do the same? Can they do this comparative analytics as well? This is Zhenghang. Hola, mi amo Zhenghang. That's as far as my Spanish goes. And he's a data scientist. So Zhenghang, he's my student. And he's a data scientist, and I'm going to ask him if he can compete with me. You know, Zhenghang is 25 years old. I am 25 years old. I'm going to compete with my professor who is a queuing theorist for over 30 years. All right? And let's see if I can do comparative analytics without understanding anything about the arrival process, the service process, the queuing dynamics. All what I know this idea of causal models, and I know some machine learning, right? I'm a sophisticated data scientist, not extremely sophisticated. I hope he doesn't listen. He's a sophisticated data analysis, and the question is, can Zhenghang, can I compete with Opher, who's a queuing theorist, and knows the system and know the queue? Okay, that's the premise. Make sense, guys, the question? Okay, so we'll use these structural causal queuing models. I'm gonna put my Zhenghang hat. We'll develop these structural causal queuing models. We'll basically use them to build a Monte Carlo simulation. Numerical method, not a queuing Monte Carlo model simulation, though. It's just a Monte Carlo simulation, not queuing. There's no arrival service times kind of captured in this model. You don't run a queue, you don't manage the queue. And I'm going to show you how the performance of this method works. And the bottom line, an embarrassment for my prof. Don't tell him about it. I do just as well as him. I'm just as accurate as him. And in fact, I do better than him in some cases, significantly better. When he doesn't have closed form, he needs to go into approximations. I don't do this. I mean, I don't understand the system. I don't approximate it at all. I use the data speaks, and that's what I give you. And my answer is better than his. Okay, so let's see how we do this. So I'm Opher, I'm a queuing theorist. I already told you how I do these things, right? I estimate the queuing primitives, what is the lambda, what is the mu. I use them and my queuing theory knowledge, and I estimate the comparative analysis, the performance measures. Let me show you how I do this on the simplest example I can come up with. It's essentially an MM1 queue with speedups. So Poisson arrivals, exponential service times, Poisson arrivals rate lambda, exponential service times. And let's go into dig a little bit into this model and then show you how I do it. Then Zhenghang will take us through his system. It's much more elaborate. He will kind of look at the parent set to get the prediction models right. Every machine learning model needs feature coming in, and these features are the parents of the child that you're trying to predict, essentially. We'll refine this parent set. I'll explain you how to do this, and then I'll estimate what's going on, how these realizations impact the arrivals, the service, the waiting times, the speed up, all of these wonderful things, because I don't know them. And then I'm going to use this Monte Carlo simulation that I promised. Again, I'm going to show you the general thing, but I'm going to show it in the MM1 example. It's the simplest. We've done it in other examples, the GGC, for example, where I beat my prof. Okay, so we'll do that. Let's take you through this.
Sir, can I make a question, short question? Do you hear me?
Sure.
Hi, this is Marcelo here. So what is exactly the data? So I understand you have data, and in your case, you're estimating the distributions and the modeling. But what is the data that the ML approach is using?
I'll show you the data. Both of us use the same data. Give me another slide, and I'll show you the data.
Okay, thank you.
This is a critical point. And by the way, I'm going to use the best data, all the data that I need. I'm going to make it very, very easy here. I'm going to have all the data that I need. No data uncertainty, no this. Both of us have no data issues. Excellent data. But I'll show the data in a minute. Queuing theory, I've done lots of work on this over the years. Great work is the project engine work that they solve MG1Q essentially. And I have the expected waiting time of an MG1Q. This is going to be the measure of interest for us today, expected waiting time. That's what I'm going to try to do. There's many papers on queuing. I'm not citing all of them. A couple of them on learning, on machine learning in queuing. Jamal has a couple of papers on using on estimating the Lindley recursion for a single server queue out of data. And I already shared with you the two papers that we have on kind of using machine learning as well, and we will use this as well. In terms of data science, The concepts that we are going to be using, that I'm going to use, are Granger causality. The idea of this and of causal influence under interference and of G computation, it allows us to take data, temporal data, so ordered by time, going to Marcelo's question, my data is ordered by a timestamp. I have timestamps of what happened. And in this case, I can go and I find out kind of the causality, who causes whom. We use Tank algorithm from 2021 to do this. And then we can basically play with this longitudinal data with the G computation approach to change the control and go from the existing system to the to-be system with a different intervention. So that's the trick that I'm going to be using. Let me go now to talk about the event log, which is the data that Marcelo, you asked about, okay? So I have, first of all, let's make sure we understand the system. It's an MM1 system, first in, first out, single server. Arrival process is Lambda. Service process is Bernoulli, where I intervene and I speed up things with a probability P. Blue P is the policy. That's what I observe in the data. When I throw the coin with probability P and it got 0, I don't speed you up. 0, I don't speed you up. 1, I speed you up. If I don't speed you up, service time exponential with rate mu0. I speed you up, service time with rate mu1. Faster. mu1 is faster than mu0. So I call it MM1 with speed ups. The easiest case I can come up with, right? It's the easiest case I can come up. Okay, what is the data that I have? I have the inter-arrival time essentially, right? I have the time of each arrival, and I can calculate the inter-arrival time between the last arrival and my arrival. That's the ith customer. Then I have the wait time. Okay, can be 0, maybe upon arrival I go into the queue immediately, but I have the wait time. Then at the end of the wait time, I observe the action, fully observable, no missing information. I threw the coin, I see the coin. The coin is 1, I'm going to have mu1. The coin is 0, I'm going to have mu0. And then once I throw the coin and I know what is the service time, speed up, no speed up, I observe the service time. Okay? So I observe all of these things for every customer, essentially. This is the ith customer. You can think about the ith minus 1 and the ith plus 1 and so on. Obviously, some of them falls in the middle, right? The I plus 1 wait time kind of possibly end here, the service time possibly end there, right? They're kind of, well, the I minus 1 service ended here, essentially, because it's a first in, first out there. All right, but that makes, I have them recorded on time. Marcelo, does this make sense in terms of the data I'm using?
Yes, yes. So you don't observe the P, you observe the action only, for example.
Yeah,
Right,
and
so
for now, I also know, I know P. As a queuing theorist, I know P as well.
Okay.
The data scientist knows nothing. As a queuing theorist, I know P as well.
Okay,
I know it's exponential, I know everything. My data scientist will know none of this. He will have the data, right? Zhenghang will have the data, but he knows nothing about all of this. In fact, I'll show you two results. I'll show you one result when he knows that it's exponential, and one result when he knows nothing. Okay, and we'll compare both of them to see kind of what he loses from knowing nothing. Okay, and my question, this is my comparative analytics question. What happens if I change blue P to P star red? Right? So I observe the data with under P blue, and I want to see what happens when I change it to P star. I change the speed up probability to a different probability. I can pay more money to speed up more customers. Is it worth it or not? Maybe I can save money by speeding up less customers. Okay, so P star is going to be something between 0 and 1. And I'm going to see if you can tell me, given you observe data from blue P, if you can tell me something on this P star red P. Makes sense, the question? Good. Half of the work is done. How I do this, I know the Polacek-Hinching formula. And if P star is red, give it to me, right? This is the input to my algorithm. Tell me, hey, what happens in a system with P star red? That's the question. Tell you, well, lambda mu, I need to square them at some point. This is the solution. Because I don't know lambda and mu, I'm going to estimate them from the data. Your favorite maximum likelihood estimates would work well here. And rather than using lambda and mu0 and mu1, I'm going to use their hat version. The lambda hat, mu0 hat, mu1 hat. I'm going to plug them into Polacek-Hinching formula, and I have my answer. Okay? This is the gold standard, guys, right? This 30 years of queuing theory, that's what I know how to do, right? There's no better solution than this. Okay? Good. Hey guys, I'm Zhenghang again. I'm going to take you through this process. We'll do it simple. We'll do it in this simple example that Opher just showed you. Okay? Let's see how it works. So first of all, this is something we both work on together. So now, in designing of my algorithm, I use the queuing knowledge. Okay? In designing my algorithm, I use the queuing knowledge. And what I do here, I create a causal graph. And a causal graph basically tells me which variable depends on which. Okay? And when I do a causal graph for any G1 queue with first come, first served discipline, this is how it looks like. All right, so remember what I observe here as the A, the action, S, the service, T, the inter-arrival time, and W, the waiting time. This is the observation. This is my data. This is what I need. So I will start, for now, let's assume that I know everything, right? I'm just developing this algorithm with you. The first thing I observe for T, it depends on nothing. It's IID, right? T depends on nothing. It has no parents. Nothing causes T to change. It's an IID variable coming out of exponential distribution in my example, but okay, nothing causes T. The next thing I look at, so I have this density for T, if you wish, in my thought. Then I'm going to look at P, the action, right? I'm throwing a Bernoulli coin, again, IID, no parents to this action. I just put the Bernoulli distribution here. I assume I know it, P to the A, 1 minus P to 1 minus AI, and I know that it's Bernoulli. I will know this for the P star. So everybody know this all of the time. The next thing, I'm going to look at the service time. And the service time, conditional on the action, either it's the service time given the action is 0, this is with probability 1 minus AI, and the other one is with speed up. So either it's with speed up or without speed up, depending on the realization of my service time. So the parent of the service time is the action, right? So I have an arrow taking from the parent to its child. Right? This is the feature. If you want to estimate the service time, I tell you, well, the feature you need is the action. If you know the action, you have a well-defined estimation problem. You can think about, oh, what happens if I don't know the action? Good question. I don't care about it. Currently, we both know the action. Okay? Then going back to Marcelo's question, I observe it. Okay, so now the next thing is W's, right? And I can basically write the likelihood function of my data. So I just wrote the likelihood function of my data, my n observations. I observe arrival time, I observe action, I observe service. The trick is now to go into estimating the waiting time. And the waiting time has more parents. The waiting time of customer 3 is the waiting time of customer 2, the service time of customer 2, and the inter-arrival time of customer 3. I know this, the Lindley recursion written here, one of my favorite tools, is well known. You can write it down. I know who are the parents of the waiting time. I can do that. Okay? So now, if I know all of this, Zhenghang and I are working together, Zhenghang and Opher are working together, I can do whatever I want. I know everything about the system, and one of the things that I can do, I can replace P blue by P star red, right? And this system, we know everything. So I can numerically run this thing as much as I want. This is the miracle of G computation, and it will converge to the right expression, right? I'll run it to infinity. I create the data. I'll simulate the system. This is my Monte Carlo simulation. No queuing, right? The Monte Carlo simulation. I can run it to infinity, and I get the gold standard, essentially what Opher got. He has this nice closed form expression. You can take derivatives of. I don't. I only have numerical method. Takes forever to converge, potentially, but gold standard. This is as accurate as can be. This is, to some extent, the most critical part. When Zhenghang and I work together, we can devise this data-driven numerical method that takes you to the exact right solution. This makes sense, guys? This is really the most critical part. Everything else, after you understand that what I do and what Zhenghang do leads us to exactly the same result. One of them is better because it's faster in its closed form. One of them is annoying because it's numerical in the MM1 with speed up example. Once you know, oh, both of them are essentially the same result, now I can try and relax all of this knowledge that I put here on the table. Right? So this is the key issue. This is our main novelty of the structural causal queuing models. I can take a queuing model, I can put the structure. And if I know this structure because I'm a queuing theorist, I can do a numerical Monte Carlo simulation that will take me to the exactly right answer. So Zhenghang can do. Now the question is, what happens when Zhenghang doesn't know all of these things, right? So that's the question. Now he will have to kind of, estimate the density of the inter-arrival time. He doesn't use its exponential. Estimate the density of the service times, given 0 and given 1. And estimate the Lindley recursion. I don't know, he doesn't know the Lindley recursion, right? How WI is. Once I realized all this data, how it is related to the WI, right? I will take his hands, I will tell you, hey, Zhenghang, forget about everything I taught you. Without knowing this, what can you do? Okay.
Opher,
So
can I ask a short question?
Sure, obviously. Yeah, this is the most critical slide. If you don't ask questions on this, I'm lost.
So this likelihood function that you have here, you're not using it for estimation. You're using it for simulation. Is that right?
Yes. So I'm going to estimate each one of the components of this likelihood. I'm going to estimate them from the data, and then I'm going to use it to create my numerical simulations.
Okay, so you're going to sample basically from this likelihood when you sample the value.
Yes. Good. Okay, so the first thing I need to do, I want to see who are the parents of any realization, right? Now, the good thing about this system, I have these timestamps, and we have lack of anticipation. Something from the future cannot impact me, right? My parents can only be in the past, right? So that already restricts what I need to look at in terms of parents. What are the important features for my predictive model, if you wish, right? So I look in the past, I find out my potential parents, and then I run this wonderful Tank et al. Algorithm to find out which one of them really impacts me, right? So it allows me to refine the parents, and when I run it, I find essentially this causal graph. So it's easy. Thousand observations, even 500 observations are sufficient for me to run the Tank algorithm on my past observations and find out essentially this structure. A and T are independent, S depends on A, W depends on W minus 1, S minus 1, and T. Just I run the algorithm and it gives me the right parent set, essentially the right causal graph. Okay, that's the most critical part. And why does it happen? Anybody who works with causal graph in reality, it's a disaster. You don't understand whom control whom. X control Y or Y control X, you don't know. This is a very simple model with this temporal part. And in those very simple stylized model, things are simple. The data is simple, the model is simple, the causality structure is simple. The Tank algorithm runs and finds out exactly the right structure. The first observation.
And the causal graph is generated through just the inter-arrival times and the service times you're generating?
Yes, so I just observe the data, right? I observe the arrival, service times, I observe the waiting times in the process, right? The action, and I run the Tank algorithm on this, and it essentially gives me the right causal graph. Tells me who depends on whom. Now, guys, this is a little bit annoying. If you think about queuing systems in general, one of the things that makes them hard to calculate, why my advisor put 30 years into studying them, is those busy periods, right? So when you think, oh, I'm the 10th customer in the busy period, Juan Carlos was the first one. and his service time impacted me, right? This is what we have in mind. But the Lindley recursion tells you, yes, his service time impacted me, but not if you give me my parents. Juan Carlos impacted my parents, but given my parents, he doesn't impact me anymore. WI minus 10 doesn't impact me anymore. Even if we're in the same busy period, it impacted WI minus 1, and all what I need to know about Juan Carlos' impact on me is captured through WI minus 1. Right? That's the key observation that allows us to do this analysis in the queue and gives me only one parent essentially. It's not all my busy period, right? Think about multi-server queues. It's even more annoying, right? Because we have several, 4 of us are servers. I need to know which one of the server you're going to, blah, 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 right? But still, once I know the last customer that entered each one of the service times, I'm done. I don't need more than. Okay, so this is the first thing. Read the paper if you want to see how we do it in more detail. The second thing, I have the likelihood function, right? And rather than using the exponential function like I've done before, I'm going to use, as Marcelo suggested, I'm going to look at my inter-arrival time. From the empirical distribution, you fit whatever you want to fit to this, or you just use the empirical distribution for that matter, right? And this is how I will take my T, my inter-arrival times. I'm going to do the same thing with the service time. Okay? And P star, I don't need to know blue P, right? I only need to know P star, red P star. I don't need to know blue P. I don't use it at all. That's what the G computation tells me, and it tells you, hey, I took blue P, I put P star red, I'm consistent. I'm still at the gold standard. Okay, so I can do this. I fit the likelihood function, and then I fit the Lindley recursion. Again, it's a simple machine learning algorithm. It's a ReLU function for those of you who know machine learning better than me. Very simple. We run it with a more complicated, kind of robust neural network. I think 64 neutrons or something like that. Neurons, 64. But it's a very simple, you minimize the mean square error, you check out of sample, and because it's a simple ReLU function, you catch it. You don't miss it. This is the work of Jamal that I mentioned earlier. They've shown this. Okay, so now that I know all of this, what I'm going to do, I'm going to create, as Marcelo suggested, I'm going to create my TI, AI, and SI from this likelihood estimation based on the empirical observations that I have. I'm going to calculate WI for this customer based on the function that estimated the Lindley recursion, my F hat W, my machine learning algorithm that does this. I'm going to pick up all of these WIs, and I'm going to save them, average them, and this is going to be my W bar prediction. It's going to be the prediction of the weight. So the process is simple, and let's see how it works, right? That's the key. This is how it works. This is MM1 with speed up, lambda equals 1, mu0 1.1, mu1 2. P blue is half of the time the speed up, half not. Guys, this is important for my data. I want to observe the slow service and the fast service often enough. If I only observe 1%, 5,000 customers, only 1%, I only observe about 50 times, my estimation of the empirical distribution, my estimation of mu1 is going to suck. So I cannot do much with it. So we have an easy question. And it doesn't matter, it works the same on the other. And you have here the errors in prediction P star between 1%, 10, 50, 90, 99%. From the queuing theorist approach, this is me, blue, and the data scientist, parametric, when I know that everything is exponential and I know the Lindley recursion, and non-parametric, when I don't know exponential and I don't know the Lindley recursion. Okay? And you see the errors, first thing that you see, all errors are very similar. The queuing theorist doesn't beat me, right? Near half, we all do very well. This is what we observed essentially. So we are predicting in this existing system. When I go to the right or to the left, my prediction power is a little bit lower. And when I go to the left, utilization is high. So everybody remember how the MM1 waiting time looks like when rho is very high. Every small mistake in rho will have a lot of impact on my prediction. So why am I 20% off here as a queuing theorist? Why am I 20% off here? Where the system is with a rho of 98, with my lambda mu0 mu1, I estimated as 97.5. This is a big mistake. So I'm 20% off. And the data scientist is doing a better job here. This is random, right? We all aim, the key issue is that we all aim at exactly the right element. And I know the right answer here because I know the MG1. I know the real lambda I knew the system. Right? They don't know it. The Opher or Zhenghang don't know it. Right? We know. So that is what we see. Now the trick is I can do it with the GM1, and as a queuing theorist, I don't have a closed form solution for GM, right? I have some really good approximations with the purple one is a heavy traffic approximation. I expect it to work well, high utilization. I expect it to be lousy at light utilization. So clearly I would not use it here, but just to show you kind of what we see, right? Errors, well, bottom line, Zhenghang, my students, data scientist, who knows nothing, non-parametric. This is the non-parametric, he beats me. Okay? He does better than me. I can show you more results, say on GGCQ, same thing happens, right? I have my beautiful approximations for GGCQ, I can use them. You know, in heavy traffic, they work fairly well. In light traffic, they don't. And Zhenghang beats me.
And how easy is it actually to make those causal graphs? Do you make a lot of mistakes or never make any mistakes?
That's why I said we never make a mistake here, which is only due to the fact that the real causal structure is very simple. Right? Whenever the causal structure is more annoying, I don't know, right? But that's the thing. To me, the way I've looked at causal modeling before is they always look at these really complicated systems. So Mark, our co-author, he's a Berkeley prof. He does this kind of in the context of medications in healthcare with experimentation, and those are kind of huge things, lots of data, many features. I don't know, you cannot get the causal graph. You cannot get the right one from the data. This is a very simple thing. Now the question is this bottom-up approach, how far can I push it, right? I show you MM1 with speed up with the explanation. GGC is very, very similar, a little bit more advanced mathematics for the queuing theorist approach, but the bottom line process for the data scientist is very, very similar and it's on the point. Well, on that point. You don't need a lot of observations here. 500 observations is not enough. So in those simple models, finding the causal graph is very easy. And remember, our stylized models, I'm talking about as a queuing theorist, but you want to do inventory, you want to do revenue management, whatever. Our stylized models are very simple, right? Otherwise, we cannot analyze them. So in those stylized models, if you give me the data, I'm good. Need to run it, but in our examples of queuing, it's good. We never missed. We never missed. We didn't screw up with that. And look, the main bad thing that can happen is that you add another noisy parent that you don't really need, right? So the way we choose where to stop and how many parents to use, it's critical, but it's simple. You see in the paper, it's no question that these are the right parents kind of when you run this. Good question, thank you. Okay, so this is, by the way, I solved the GM1. I don't know how to solve it. The ground truth here is from my first paper on the GG1, the machine learning. And I told you I'll get back to it. Good. So that's the bottom. The bottom line is when I use this kind of structural queuing causal models, me and Zhenghang, we both do about the same. Unfortunately, he even beats me in some context, which is quite frustrating. The guy's 25 years old. I've been a queuing, right? So the queuing domain knowledge doesn't help you, which is why did I start the project? Right? I started the project to come to you and tell you, hey, you need to know queuing, you need to know the model, you leave on the table 10% accuracy or whatever percent accuracy. Right? This is what I envisioned the project as doing. And I'm kind of, right? I'm hitting my head because it doesn't. So not good news for me as a queuing theorist, especially as one who works with data more and more. Okay, wonderful. How much time do I have? I think I ran really quickly.
Well, it's on the sharp, it's 10 minutes more, but we can
10
extend it
minutes
a bit
more.
more.
So let me summarize quickly this, and then I want to show you a demo from SiMLQ. It's 5.5 minutes, and with a couple of questions, it will take about the rest of it. But what we've done, I talked a little bit about management analytics and this kind of descriptive, predictive, which is easy. 2 Nobel Prize that talks about causality, taking you to comparative, right? 2011, 2021. Comparative, prescriptive, which is what we want to do, right? I want to use data-driven decision-making, prescriptive analytics, the optimization part. My friends in econ don't understand what I'm talking about. It drives me nuts. Comparative is prescriptive. Oh, I know how to compare things. No, this is not enough. You need to choose. It's not simple. The choice is not simple. They don't care about it. They are in the prescriptive part. Their prescriptive is, oh, you have the prescription. Yeah, but why do you give me the prescription? This is one option, right? Let's optimize. They don't understand this, but here we understand. We talked about machine learning for queuing models. I think it's a promising direction. It's a little bit of brute force now. I've seen better work that can look at where do you sample a little bit more effectively, and also use the exact results or approximations in the right places to kind of decrease what we need to do. I feel we will be able to push the solution of simple stylized queuing models further using this machine learning algorithm. I talked about causal queuing models, where Zhenghang, my student who couldn't come with me, apologies, who knows a little bit more Spanish than I, basically beat me and show you how he can get better results than me without knowing queuing theory. Zhenghang knows queuing theory, right? He's my PhD student. He's not getting a free ride. But when we run this algorithm, the data scientist work, he kind of ignored it, right? And it works as you kind of question very, very well. What I want to show you now is a little bit on SiMLQ. This is our startup. Showed you the 8 people that work there. One of them switched since, but there's another one that two more people that I didn't show. They're data scientists and the junior programmer, and the senior programmer. So 3 people I didn't show. But let me take you through this demo. I'm in the wrong. No wonder I cannot show you. Guys, this is the demo. Can you see it? You guys see it well, right?
Yes.
I'm going to play it. I'm going to stop it at a couple of places to add context. This is real data from an emergency department in Toronto. This demo is almost completely real time. We cut 20 seconds runtime of the simulation in 2 places that you'll see well. I'll show you just to make it a little bit shorter, and right? But it's almost real time. The key issue is that the simulation model, to find the simulation model takes us seconds, 3-4 seconds, and then running a simulation takes time. It's computational. Okay, so.
Hello everyone, and welcome to this SiMLQ demo. Before we load data into SiMLQ, let me show you how a typical CSV event log looks like after some pre-processing. So an event log is nothing but a list of events happening to cases over time. Cases, or you can think of patients, have an identifier, which we call the case ID. They go through activities such as triage, registration, assessment, etc. And we have the timestamp when this activity started. In addition to these 3 basic columns, we have additional attributes like initial zone, the zone to which the patient was assigned, the age of the patient, the gender of the patient, and their triage description, which is how urgent the patient is, as additional columns that help us build better digital twins or better machine learning models. Going back to SiMLQ, we will now upload the CSV file, and we need to tell SiMLQ which column is the case ID, the activity, and the timestamp. In addition, we will choose initial zone, age, gender, and triage description as attributes that would help our machine learning models build a better digital twin. Loading the data in, the first thing we get is a process map. So we see that 2,750.
So this is descriptive analytics. This is what I observed from the data. And I can tell you, hey, this is how the data behaves. This is a little bit clean, right? We cleaned for the demo. It's a simpler description of an emergency department, but this is what's in the data. And you see, I get it in no time. Essentially, immediately I get the process that generated the data, essentially.
52 patients start at the beginning, go through triage, registration, assessment, and here we can see some of the statistics for each station. Assessment, for instance, takes over 2 hours on average. Some of them, 322, go through consult request and consult arrival, but the vast majority after assessment continue straight to disposition. And all the patients are eventually disposed and go to queue end. Now going to the dashboard menu, we see various performance metrics such as length of stay, the time to physician's initial assessment, the time until a consult arrived, and additional statistics.
All right, so what we see here, a built-in KPIs, the length of stay in the system, and user-defined ones. In emergency department, time to initial assessment is really important because we're all stressed before we've seen the doctor, and after the doctor looks at us, we feel much better. Not to mention the fact that people may die waiting for a doctor, right? So this is an important one. You need to carefully define it in those settings, and we can do it. We've done it for the demo. We've done it behind the scenes, but it's a user-defined performance indicator that you care about. Again, this is blue descriptive analytics. There's no magic other than measuring in the data what happens here. We haven't started with anything magical. Maybe it's nice, the visual dashboard and so on, but this is not where the magic happens. The magic happens in
the top. We call these the stat panels, and they show us these different performance measures. For instance, the average length of stay is 3.71 hours. The time to physician's assessment is almost an hour on average. Here we also get various histograms. We have the histogram of the overall length of stay, the histogram of the number of people in the system. This is the crowding of the hospital. And we have time series, the time series of the number of people in the system, and the arrivals time series, how the arrival rate varied over time. Now we can use these statistical dashboards to drill down and find the bottleneck. So if we look at, for instance, how long it takes to register a patient, this takes approximately 45 minutes. We know from this process the assessment station is much more problematic as it takes more than 2.5 hours until the patient gets assessed. Therefore, we will go back to the process map, and now we'll create a simulation model of the system. First of all, before intervening on the system, we need to create a digital twin, a high-fidelity digital twin, and you will see that this happens in a matter of seconds. Simulation was completed, and now we can compare head-to-head the original data with a baseline simulation model. You see that in a matter of seconds, we learned the digital twin from the data, and we simulated it, in this case 10 times, in order to be able to compare how well it fits in terms of the different performance metrics.
This is magic number one. This is predictive analytics. I look at the system, and I generate numerically additional sample paths that looks like the system. If you've noticed, when I upload the data compared to the data I use in my causal queuing models, where I have arrival time, service time, waiting time, here I only had arrival times. I didn't have service and waiting time. It's unobservable. With this missing data, 2 weeks of data, only 2,700 patients, look at the fit. It's very good. So this is magic number one, our ability to come up with this missing data. Not a lot of samples. 2 weeks. This is not a long, right? Emergency one. Very good fit. Obviously, more data, better, less missing data. We'll have a better fit. But again, for the demo.
And we see that the fit is pretty astonishing. The length of stay is very close on average. The median and the 90th percentile. Same goes for the physician's initial assessment time, the time to consult, and the various statistics. We see that there is a very good fit on the histogram side as well. And this is the first magic of SiMLQ, being able to build a high-fitting, high-fidelity digital twin in a matter of seconds. Now we go back to the process map because we know that the assessment station is a bottleneck station, and we're going to intervene on that station and make it 50% faster, and that will show us what is the impact of this intervention on the overall process. And this is the second magic of SiMLQ. being able to step outside the current model, outside the current system, and propose a 2B model that will represent the system of tomorrow, an improved version of the current system. The simulation is now complete, and now we can compare head-to-head the original data, the baseline simulation data coming from the high-fidelity digital twin, and the intervened model simulation data, which is the digital twin under an intervention. Now, if we trust our digital twin, we can disable the original data to improve the visibility of the differences between the two systems. And now we can compare the length of stay before, which is almost 4 hours on average, and the length of stay after intervention, which is under 3 hours. We see an improvement in every performance measure in the system. And
so this magic, this is the real magic, me being able to step out of the current system, descriptive, predictive, to a different system with different capacities, essentially, doing the comparative analytics, getting good predictions. The causal queuing network model behind the scenes allows me to do this jump, essentially.
And here, when you're switching that station to a 50% more efficient, you're moving the complete distribution, or you're just cutting at the 50th percentile up what you're doing?
I basically divide it by half. So my machine learning model told me 1, 1, 1. I move it to half, half, half.
So you're displacing the.
I'm basically dividing it by 2. I'm splitting it up. You want to do it differently, we can do it differently. This is not a thing. The main magic of this is if you were 1 hour, you were 1 hour, and you were 1 hour, you arrive the minute apart, 3 hours in the system. Right? In queuing, when I cut it to half, suddenly you 1.5 hours in the system. You're not just 2.5 hours in the system, right? That's why queuing models are tough, because we depend on the busy period, right? We depend on the busy period. This is what I can capture with SiMLQ. This is a simulation model, a queuing simulation model, not the causal model that I've shown you before. But the train of thought is very similar. This is once I have the right causal model, I can run the simulation and I can get you the solution. Make sense?
this is the third magic of SiMLQ. In minutes, we loaded the data, we explored it, we found the bottleneck station, we created a high-fidelity digital twin, and we were able to propose an intervention that improved the process. And imagine that we can do it on every data set, every event log coming from your organization. It can.
So this is really the magic, right? The magic is, you saw how quickly I'm doing this? This is 5 minutes of work. I did it on an emergency department data. You run a hospital, you have a walk-in clinic. I can do it in the walk-in clinic. You have operating rooms. I do it on the operating rooms. You have wards. I do it on the wards. You have financial processes. Patient came, I put out an invoice, and they paid me a month later from the insurance 80% and 2 months later from the patient 20%. It's another queuing network. The financial system, same thing works. Once you have this tool, you upload the data into it. It's a data-driven tool. The data needs to be sensible. But the descriptive analytic parts, which I ignore, they say, oh, they're easy. This is what allows me to also look at the data and make the right data. I always say there are five processes. There's the design process, there's the real process, there's the process in the data, there's the process the domain knowledge think is the process. The people, the experts think that process is. They don't know either one of the other ones. And there is the optimal process, where I want to go. The descriptive analytics allow me to kind of look at all of this and not converge like completely, but make them closer to each other. And the comparative and capabilities allow me to now start investigating in the prescriptive one. I don't have prescriptive capabilities here, just comparative as I showed.
And here you're looking at the activity. You're
yes.
talking, what about, does it have the capacity of resources also?
Yes. So in this demo, we haven't used it. Again, just to emphasize how strong is the algorithm behind SiMLQ. But if you tell me, look, between 9 a.m. and 4 p.m., there are 3 doctors and 5 nurses, I'll put it in, and then I can change a doctor or a nurse, right? I have the causal model behind it, and once you change it, I will show you how things go. Another things that we've done, with the emergency department example here I'm using is because we have a pilot with an emergency department, and what we asked them to do is to change the routing. So they had about 30% of their acute patients going to the rapid assessment zone, and the rapid assessment zone was kind of idling sometimes of the day. The non-rapid assessment zone, the main room, was always busy. The rapid assessment zone from time to time would be empty at nights, essentially. Say, hey, move more people, more acute patients into the rapid assessment zone. So they moved from 30% to 45%. We now have this beautiful matrix of 2023, 2024 real data and under the different intervention. And we can show you, given the simulation, what would the intervention is at. We can do the counterfactuals essentially on each one of these places. And you can see that it moves in the right direction. So yeah. Guys, so this is my message to you, that basically there is much we can do with let me go a couple of slides forward. There's much we can do with queuing and data today. There is much we can do using machine learning, kind of adding it to the point. I find that the way we think about the problem and model it is critical to be able to do these things, right? So I feel that operations research, what we bring to the table is our modeling ability and our understanding of these stylized models. So the features that SiMLQ is using in order to show you these wonderful things, which I don't publish because they're patented, right? And this, you need to know queuing to do that. You need to know queuing to get those features to allow you to have these magics, right? And to me, again, I'm looking at our students today and I think about these guys sitting in the C-suite 20 years from today, when they'll be as old as us. And right? And I said, they'll use this tool because I can do it. And if you can do it, why not using it, right? So you use the data-driven tool and you can get really a digital twin of the system, and you can quickly have a discussion between the digital twin and reality. You change reality because I made some recommendations, the data change, you give it to the digital twin, I update the digital twin. I have quickly I can update my model, then I can tell you what to do next, right? So this discussion between the real system and the digital twin, which we cannot do today because it takes us to build a simulation, takes us a lot of time to build. If everybody that's run a simulation, it's months until you get it right. Right? So you cannot have a digital twin. We have a simulation model. What I claim is with this methodology, we can have a digital twin such that we'll have this discussion. Change the system, change the digital twin, change the system, change the digital twin, and it takes seconds to do that. So that's my message. Thank you, guys. It's a really pleasure.
Thank you. Thank you.
Some questions, please.
So this sort of remembers me a lot of process mining.
Yes. So the engine behind going from the data to the map is process mining. And the engine pushing it forward is what we call queue mining. So Arik Senderovich, one of my co-authors and the co-founders of SiMLQ, his dissertation was the pioneering work on queue mining. He did it with Avishai Mandelbaum and Avigdor Gal from Technion. And that's what we basically build upon this. So Arik came to my office. He did his postdoc at University of Toronto and he said, hey, let's do something together. Let's do some research. And we started writing on the whiteboard. And at some point I said, you know, among all the things that you know how to do and the things that I know how to do and the things Dmitry knows how to do, we can go from data to simulation model. So data-driven simulation. And I told him, this is not a paper, my friend. This is a company. This is not theoretically, I didn't prove anything, right? There are nice features there that I can write a paper on, I'm not discover, right? But this is a company, this is not a research project too. And because I feel there's enormous economic potential to this method. I don't know if our tool is going to be the tool of choice, right? Our vision is SiMLQ as the tool of choice for digital twinning in all of these industries that have queuing networks in cloud computing, manufacturing, logistics, healthcare, e-retail, financial ones, right? Justice systems. right? All of these wonderful things. And you can do this, and there's value in doing this. There's value in being able to play and do the comparative analytics. We know optimization well. Once I have this engine to do comparative analytics, putting an optimization engine on top of it, running the right interventions in a smart fashion is not very tough. We haven't done it, but we know how to do it, right? You give me the KPIs. I need the PIA to be below 2 hours, 90% of the time. I tell you how much capacity you need to add and where, right? The trick in doing it in a scalable fashion, automatically, I need the cost. So the cost in your hospital, the cost in my hospital are not the same. The data in both hospitals is the same. The costs, I don't know. You have a union, you cannot change the nurse staffing. You don't have a union, you can change the nurse. I don't know, right? So the prescriptive is a little bit harder, but a solver, right? We all use solvers. Solver is a tool easy to use, and I need the comparative analytics at the engine that I get from SiMLQ to do. So yeah, I'm
very nice, very nice.
Thank you.
Thank you. Thank you.
Sure.
I saw you, thank you for the presentation. I saw you use long short-term memory. Did you try any other machine learning model, or did you just got those wonderful results?
No. We tried other things. They didn't work as well. So the idea of large language models and how they're being trained should have worked better here, but from first experimentations, it didn't. So the LSTM worked better. So that's why we continue with that. Now, could I play with the hyperparameters a little bit more and get better results out of there? Yes, probably. But you know, we have to choose something. We looked at both of them and said, this is doing much better. So why should we bring a heavier hammer? Right? I mean, I don't want to use I want to use a simple tool as possible. This is science, right? Explain to me with the simplest tool as possible. Yeah, I can bring more complicated systems, things there, but there was no benefit. So transformers, right? We run it with transformers. It's not even as accurate. So why should I use transformers?
I got your point. So if it works, it's fine. But do you use any knowledge from queuing system to fine-tune the model, or just like?
No.
So any knowledge to fine-tune the?
So.
Just data science.
Yeah. No. I mean, again, the features that you want to keep from your short-term memory. What are the features that you need to keep? This is queuing ones, but in essence, it wasn't very groundbreaking. It's the distribution, right? You tell me what's the distribution of now, your predicted distribution now, and let's remember it for the next time, right? So I start from a given distribution, and I update it and update it and update it, and I want to use the last one, not the first one, essentially. And so there's not a lot of magic there. That's why I said it's. I mean, this is a paper. On the one hand, I feel it's an important OR paper because it takes a very fundamental question and solving it with new tools that are very fundamental again. On the other hand, theoretically, I mean, there's nothing theoretical groundbreaking in this. We send it to, I think, computers and OR. So the paper is there. I mean, I want to do an OR work, but this is not the right thing. It's more a computers and OR. So that's why we send it.
You're solving a real problem, and you're solving it fast. So it's
that's the right outlet, right?
Thank you very much.
Thank you.
Thank you. Wonderful. Great work. Yeah.
Thanks.
I'm using right now that because I'm doing process mining.
Oh, good.
So it's actually we're working with here in the government, they're, it's a process where they're working, so what they're doing is actually, they have all the logs of the process they have.
Event logs.
I put it on Disco. And then afterwards, the big question is how many servers or how many people we need to put in order to reduce the times stuff and.
Yeah, so I think the key issue of SiMLQ is really the ability to answer these questions in a more meaningful fashion.
Because right now, what I have to do is I have to take the process from Disco and put it on a simulation.
Yes, but you build the simulation model for it manually. I build the simulation model. So I take the data from Disco essentially, I put it in SiMLQ, and get the simulation.
Exactly, yeah, it's
Right,
wonderful.
so that's, yeah. So it's
Good to see you.
good to see you again, yeah? It's,
Say hi to Dmitry.
obviously, Oded is retired, right? So
Yeah, well, I saw him last time in a